So indeed, my presentation will talk about an experimental investigation on the notch strength of lamellar cast iron. Before starting, I would like to acknowledge my co-authors from Movares, which is an engineering company in the Netherlands, and my colleague from DOE. So the context of this research is essentially related to railway canopies, which are these pretty long structures located in some railway stations in the Netherlands, and these are considered historical structures because indeed were built a couple of 100 years ago, and they are all made of lamellar cast iron. Now, columns, and I mean, generally cast iron is a material, especially lamellar cast iron, which is very strong under compression. It's comparable to high-strength steels, but under tension, it doesn't perform that well, as we will see. So they were worried essentially because of the presence of holes along these canopies that were made through the years, because during the use of the structure, to attach some, to have some attachments, for example, for screens or signs, stuff like this. So when they essentially found the holes, they started wondering about indeed the stress concentrations and so on, even though you might think that these columns are loaded in compression for a very strong material. A hole will not be such a problem. Well, if you consider that these are very long structures, it could be it could be also 100, 200 meters. During the summer hot days, the elongation of the canopy, so the elongation along the direction of the track, could induce some substantial bending moment to the last columns, and in some cases could cause fracture of the column due to bending. So I mean, this is within the context of bending strength of cast iron. If you look in the lamellar cast iron, well, if you look in the literature, it's a very controversial topic because especially a couple of years ago, a couple of 100 years ago, they were essentially coming up, engineers and designers, with optimized cross sections, with each and other cross section based on experimental investigation was coming with a certain ultimate load depending on the cross section, because in fact there is no stress-based criterion that can be used to quantify the strength of this material. So in our work, we performed a material characterization of the material of these canopies and characterization of the notch strength in tension, as you can imagine, for what especially concerned the worries of the engineering company, and then a derivation of the sign value of strength. So the peculiar behavior of lamellar cast iron is essentially due to its microstructure, because it can be made from either a ferritic or a perlitic matrix, depending whether it's a ferritic lamellar cast iron or perlitic. But the very, let's say, characterizing aspect of this material is the presence of these graphite flakes, which act like, they're very thin, very hard, and they might act, let's say, they open during tensile loading, and they instead react reacting in compression, instead contribute to the stiffness and to the strength. So that's explained one of the reasons why cast iron, lamellar cast iron, has this difference in tension and in compression. So we performed some tensile tests on coupons extracted from each and every column, and yeah, we essentially came up with stress strain curves. Now, what you can observe a few peculiar aspects is that the Young's modulus is way lower than steel, is half the value, is 100 gigapascal, and you may not be able to define a yield stress, because sometimes it can happen that the ultimate tensile stress occurs below the 0.2% residual residual stress, residual strain. So, in fact, usually for this kind of material, in standards that are used to characterize and categorize the material, usually it is referred to the 0.1% residual stress. And within one column, the material behaves pretty much uniformly, but there could be quite some scatter from column to column. It's very dominant, although this was the same foundry and that produced this material back in the time. So just summarize here what I just mentioned about the variability of, for example, the ultimate tensile strength, within batch variability and in between batch variability. When we look at fracture surfaces, well, if the specimen had, let's say, if you could test the specimen and you don't find any defect, then you are able to reach about 150 megapascal of ultimate tensile stress, and the fracture surface appears like this, very crystalline, transverse to the loading direction, the material behaves fairly brittle, and there is no sign of necking, yielding, no gross plasticity takes place. But for some specimens here and there, we found the presence of casting defects. You can see here what we think is a shrinkage porosity for a specimen that eventually failed at a lower value of the strength of stress as compared to the others. Then we performed also compressive stress on cylindrical specimens. Well, we use also strain gauges to quantify the strain. And you can see here instead the very high performance of the material when in compression. While bringing these two curves together, we also quantified Ramberg-Osgood parameters. But bringing the two curves together, you basically see 150 megapascal was about the ultimate tensile stress in tension. Well, these curves are extrapolated, so they're not. You shouldn't take them as they are. But in fact, the tension and the compressive strength are completely different. We have about 150 megapascal for the tension and about 500 for the compression. So then we made a second test series with the specimens having essentially, so they look like a tensile specimen, they're a bit bigger, and there is a notch in the center of the specimen, a hole, a simple hole, and its specimens are made such that the net section area is constant. So that, because basically, well, we are in Eurocode-driven kind of approach, you will calculate the net section stress and multiply it by the ultimate tensile stress in the net cross section as a failure criterion. So we said, okay, let's keep this constant in such a way that the stress concentration, the theoretical stress concentration factor, ranges within 2 and 3, roughly 2.2 and 2.8. We're a bit limited by the dimensions. Together with this, we had a test series of larger specimens as compared to the coupon test without a hole, because we wanted to see, and that's something that I will briefly mention later, we wanted to see whether the size of the specimen could actually bring in a higher chance of having defects here and there. So if actually with larger specimen, there were more specimens that we actually had to reject from the analysis because of the presence of defects. So you can see here two typical tests. In this case, one that, let's say, went well, where, well, you don't see that very clearly, but here the fracture occurs, I mean, at least the trigger point of fracture is at the root of the notch. Instead, for these other specimens, that is not clear here, but luckily I had another picture, you observe this crack path. Well, you can imagine the reaction when this thing occurred at the first glance. But in fact, the reason for that was a shrinkage, again, another type of casting defects, close to the hole that indeed induced this curved crack path due to the stress distribution. You can imagine the crack will follow to the hole, and then eventually the second ligament snapped. So in the end, we could summarize, let's say, the good test results, so those that were not affected by the presence of defects. So we can see that when there are no defects present, the tensile coupons have more or less the same strength of the large coupons without a hole. Well, this is just something I can mention to you. I didn't bring the results with me, but in this case, the number of specimens that we had to reject was way larger than in the case of the tensile test. So yes, a larger volume of testing, a larger volume of material significantly increased the chance of finding a defect. Therefore, yeah, in this case, we have to reject more specimens. But nevertheless, statistical significance is such that we can pool these two batches in one, and more or less we observe slightly the same trend for the notched specimen. Apparently the severity of the notch in the linear elastic regime did not contribute so much to the strength. Actually, we see that the specimens with a higher stress concentration factor, it appears there is a slight upward trend, as if the gradient of the stress field could actually be also a driver for higher failure load, actually. So higher gradient, slightly higher failure load, which is in line with what in the literature has been observed in bending, because they talk about an overstressed depth, as if locally the material in the presence of a gradient could actually exhibit stress higher than the ultimate tensile stress. But nevertheless, the statistical significance is also negligible, so we decided to pool these data series together for this at least dimensions range of holes that we examined. Worth mentioning that if we come up with a characteristic value, so 5% probability of survival for the ultimate tensile strength, and we would apply that as a failure criterion, considering a net section area for the notched specimen, this will not be a successful approach. So then we pooled indeed, you can see here the two pooled data series with some statistics, the mean, standard deviation, coefficient of variation, and number of samples that are used to come up with these statistics. And then we followed the approach in the Eurocode 0, the Annex D of the Eurocode 0, which is design assisted by testing. So essentially, you can come up with a design value of strength to use for actual design. And this is the equation for coming up with the design value. You can see here a factor eta. Eta is essentially a conversion factor to account for different utilization. It's a bit controversial, but you might think of it as if you are testing slightly different condition than the structure will actually experience in service. So if you're testing what you think it's a similar condition, then you can keep this value to 1. Otherwise, you should apply a penalty or something like that, or an allowance for a larger value in case, you are testing, for example, a worst case scenario kind of thing. But if you consider an hollow column in bending, well, we can imagine that on the wall thickness, we could imagine something like a uniform stress distribution. So eta for us is equal to 1, and then there is essentially this kappa value, which is related to the student distribution, to the non-central student distribution, and we see two opportunities in the Eurocode in case the standard deviation or the coefficient of variation was known or unknown. Well, we are in this case. And depending on the number of specimens that we tested, we picked the interpolated value here for kappa. Coefficient of variation is unknown because it has been obtained from test data, so we didn't have other test series that we could use to quantify the scatter of the strength of this material. So yeah, it's a bit more penalty because in fact you lose a statistical power. In the end, we needed to decide which consequence class to apply to this structure, depending on the essentially the consequence of failure. Normally, railway canopies, this kind of small structures, are public structures, so they would fall in consequence class 2. You can imagine consequence class 3 will be for a bridge, something like that. So consequence class 2, okay, it's a busy, could be busy, but it's not 1 minute. It's not the biggest train station in that case. So but nevertheless, I will show you the calculation for both and then explain why we went for consequence class 3 instead. So for consequence class 2, reliability index is equal to 3.8. And to cut it short, essentially, we came up with these two design values for the strength, for notched and unnotched. And for reliability class, consequence class 3, instead, we came out with slightly lower values. So then we follow what in the Eurocode 0 is stated as essentially, you can decide for a part of the structure to apply a different consequence class than what it will be considered for the entire structure, depending on the design consideration. So in that case, we considered a higher consequence class, so a bit more safety, because in fact the design did not take into account of the presence of defects. So if it would, when they designed the column, then consequence class 2 could be desirable. But we went for a bit higher safety level. So going to the conclusion, we propose this characterization of gray cast iron in tension and compression, to perform test of notched components with the theoretical stress concentration factor between 2 and 3, more or less. We observed that the material has some degree of notch sensitivity, and this induced a reduction of net section stress to failure of about 15–20%. And this does not seem to be dependent on the notch severity, at least for the range of notches that we looked at. But we recognize that casting defects have a significant effect on the strength of gray cast iron. So as a follow-up research, we are going to perform a bending test on the columns, on the full-scale, well, almost full-scale columns, and apply some local criterion, like, for example, theoretical distance, to obtain somehow a unified failure criterion for different loading condition and geometry. And yeah, thank you for your attention.